Hello everyone. In this set of videos, we are going to look at the follow-up to the interrupt request handler that we had considered in the previous videos. In particular, we are going to look at a slightly more advanced way of handling interrupts, where we sort of break more complex work into two parts, what we call the top half and the bottom half, and sort of try and explain why do we need that kind of a split in how interrupts are processed or handled, and how we can do that in the context of the Linux kernel. So, we will be looking at how we can implement blocking I/O input output using the concept of something called a wait queue, and how we should lock certain variables or parameters that can be changed between an IRQ and a process, and fundamentally try and understand what's the difference between the IRQ handler and the processing of the data that it involves. This in turn leads us to the idea of deferring heavy work. Right. So, what do we mean by heavy work? We will come to that in a moment. Essentially anything which can take arbitrarily long, where we do not know exactly how long it can take and where it is possible that some other interrupts might in turn come while we are actually trying to do the work. Right. So, that is what we call heavy work. So, we try and split up an interrupt handler into two parts, what we call the top half, which has to be very fast and brief, and the bottom half, which does a significant amount of work. We will look at this in the context of the FIR filter example. Right, and basically use the done signal from the FIR filter as an interrupt and demonstrate how it can be used. We will also briefly discuss the trade-offs between polling and interrupts and when it makes more sense to use one versus the other. So, just to review right from the previous week's videos, what does a minimal interrupt handler look like? So, an IRQ or interrupt request is what happens when some peripheral has completed some work and wants to wake up the CPU, right? And as we saw, the chain of events is it raises a digital signal, right? Some signal basically goes from 0 to 1, typically assuming that we are talking about a level triggered active high interrupt, right? So, once that signal, whatever it is, it's just a digital I/O, it goes to 1, that in turn goes through the interrupt controller and eventually makes its way to the CPU. Now, once the CPU gets an interrupt, it's supposed to respond, right? And typically there is hardware inside the CPU which says, okay, now I've got an interrupt, I need to do something, which means that I need to stop whatever instructions I'm currently processing, save some context, right, move things around, jump to something called the interrupt handler, which in turn is defined jointly by the software, the interrupt controller, the kernel, all of those put together tell us where the interrupt handler code is to be found. And once the kernel has finished handling whatever it needs to over there, it can come back and resume whatever it was doing before that. So, in the previous videos, we saw what looks like a minimal request handler. So, just to sort of briefly review the main tasks that we are trying to do, right? It's a function like any other function in the Linux kernel. It has a specific type called the IRQ return T, which is basically a kind of integer, right? It's basically an enumerated data type. The specific number of the interrupt is passed in as a parameter to this, right. So, I need to sort of associate specific interrupt numbers with each interrupt handler, and this number can in fact be used inside the interrupt handler in order to see what needs to be done. If you look carefully at this code, you will realize that this parameter int IRQ is actually not being used over here, right. But it could be that I could, for example, share interrupts. So, there might be multiple IRQ handlers that are connected to the same interrupt line, in which case the IRQ handler needs to go in there, look whether this is for me. In other words, does the fact that I was interrupted match with the interrupt that I am supposed to handle? If it's not, it can probably return an IRQ none and basically just let some other handler take care of it. But that's sort of rare. You do that only in a case where you are actually short of interrupt pins, right? It's always better if you can actually associate separate interrupt numbers, IRQ numbers, with each interrupt that needs to be handled. So, what is it that happens inside the IRQ handler? We first read the present status, okay, and this is of course the example from the smart timer, right, is intentionally kept simple. What we are doing is just reading something from the status. We check whether the interrupt was actually correct, right, and we are supposed to be interrupted only when the smart timer has wrapped around, has basically overflowed the period, right. So, in which case we expect the wrap bit to be set. Now it's possible that somehow either accidentally or due to some other kind of either a hardware issue or a software issue, it's possible that an interrupt gets generated more than once. So it's always better that we check this, right? You check the status, you check whether the wrap bit is actually set. If it's not, then it's best to just return none and be done with it, right? But if it is set as we normally expect it to be, we clear it, right? We also do some minimal amount of work. This is the part where I actually do work corresponding to the interrupt handler. In the previous case, right, with the smart timer, all that I did was increment a counter and I return the enum value which says IRQ handled. So as you can see, this is very brief. There is no IO or in particular blocking IO, right? There is IO in the sense that there is readL and writeL. So both of those are dealing with direct memory mapped addresses. But anything else which could potentially, go into, I'm trying to read from a particular memory location, it then goes into cache, there is a cache miss, I need to pull in data from external memory, that's not permitted. You should not, not that it's not permitted, it's a bad idea to have that inside an interrupt handler, right? So anything that could potentially block, meaning that if I try reading from an arbitrary memory location, right, it's a bad idea because there is a good chance that because the thing was not present in memory, the interrupt handler basically gets stuck waiting for the data to come in. And this part of the interrupt handler is supposed to be as brief as possible. There's a simple reason for that. During the time that I am inside an interrupt handler, it is possible that yet another interrupt comes along. Maybe not the same IRQ number, maybe some other interrupt. But what that means is I will be in the middle of an interrupt handler, which is after all some function corresponding to some code. I will save that context, I will jump to the new interrupt, and then eventually I'll have to sort of pop my way back up the stack and come back. I don't want to sort of, as far as possible, I would prefer not to deal with one interrupt while I'm already processing another one, right? Because that can lead to all kinds of complications. In particular, it can lead to situations called deadlock, right? Where interrupts are typically dealing with things that are hardware sensitive. It is possible that you end up waiting for some data to be free, and because you have got another interrupt at the same time, that data can never get freed because I never get to the point of actually releasing it, right? So there are a number of issues that can happen when you get an interrupt inside an interrupt handler. We try and avoid that as much as possible. It's not completely possible to avoid it altogether, right? But to the extent possible, we would like to minimize that chance. So the work that is done inside the interrupt handler should be as brief and to the point as possible. So things like blocking IO, shared state protection is basically where you have some data which is used by the interrupt handler, right? For example, this IRQ count is technically speaking a shared state. It is used over here. It can also be read out by the sysfs attributes in order to print on the screen and so on, right? And what we cannot do is basically sort of defer an action saying that, I'll put it to sleep and come back and look at it later. There is a way of differing, meaning that inside the interrupt handler, I can explicitly say, right, I'm done with the interrupt, somebody else needs to take over and do some other work with the data that I have actually collected right now. But that is a different way of handling it, as we'll see. That is how essentially what we are going to be looking at in a moment. So this is, as you can see, a minimal interrupt handler. The only kind of IO that you have is readL and writeL. You have atomic operations for incrementing counters, all that is fine, right? Checking very basic kind of instructions, all of these are okay. Anything more complicated, you try and avoid as much as possible inside the IRQ handler. So this is sort of the crucial, point that you need to keep in mind. Handlers are supposed to be atomic. What does atomic mean? It means that the entire handler either runs or it doesn't even start. Okay, so there should be no question of part of the handler running, getting stuck midway through, and you then jump to some other code and continue there. That should be avoided at all costs. Sometimes it may not be possible. You may actually find that while you are in one interrupt, I do get a physical hardware interrupt from somewhere else and I need to handle it. But what is often done is that the moment you enter an interrupt handler, there is also a possibility in some cases of turning off interrupts, right? So things of that sort are often used in order to achieve what is called atomicity. We make sure that once we enter the interrupt handler, it is run through to completion. But that also means we need to keep them short. You cannot sort of go in there and take like seconds or minutes of processing time for an interrupt, because it means that the entire system is basically frozen during that time. It can do nothing else. You cannot even have a timer interrupt, you cannot move a keyboard, you cannot press a keyboard, you cannot move a mouse, you cannot display anything on a screen, right? Nothing else can be done during the time that you are inside an interrupt handler. Which means that, as a very sort of brief rule of thumb, there are a few things you cannot do, or should not do rather, inside an interrupt handler. It's not that you cannot, right? It's not that the kernel will prevent you from writing such code. It's just that if you do it, it's bad practice. It will almost certainly lead to complications at some point. So sleep, right? msleep, sleep, these are all functions that are provided as part of the C library, which allow the program to basically go to sleep for a certain amount of time. The CPU is freed up, meaning that it can do something else. Now what that means is, if I try sleeping inside an interrupt handler, I have lost context. I go out of the interrupt handler and start running some other function. That is something that you should not do. There is also the notion of something called a mutex, and mutex and spin lock is something that I will be discussing in a little bit more detail in a moment. We will get to that later. Now copy to user is a function which basically allows you to take some data which is present in some location in memory. Typically it could be something, it could potentially be something like maybe you got an interrupt corresponding to a network packet coming on Ethernet, and you want to take the data and copy it into user space, meaning that into an array that the user can see and handle. That's usually an expensive operation, because as I said earlier, you cannot guarantee that your memory is, first of all, in a very specific location in the, you don't know where in the cache memory hierarchy it is stored currently. Right? So it is possible that you could end up waiting for hundreds or thousands of clock cycles for this copy to user to finish. So it's an unsafe function to use inside an interrupt handler. Similarly, malloc. Of course, you cannot use the general malloc inside the kernel, but there is something equivalent called the kmalloc, right, which is the kernel malloc or memory allocation function. Once again, not a good idea to use it, because it is a potentially time consuming function. Okay. What you can do on the other hand are use functions like readl and writeL. These are sort of guaranteed because they are directly meant for direct address access and mostly corresponding to peripherals, right? And in most cases they are not meant to be cached. So they are safe functions to use inside interrupt handler. Atomic operations are things which, once again, as I mentioned over here, the whole idea of an atomic operation is something which either the entire operation completes or no part of it completes, right? Now, why would I care about an atomic operation? Let's consider something as simple as I want to do x is equal to x plus 1, right? Now, the problem with that is it looks like an extremely simple operation, but in practice what I need to do is I first need to read the value of x, I then need to increment it, add, and then I need to store that value back into x. So, there will typically, depending on how it is implemented, there could be a load, an add and a store. Unless x is directly inside a register, in which case I can basically just do the add and I am done. I don't need to sort of move it around, okay. But if I need to load it, add it and then store it, there is a possibility in a multi-processing system that in between the time that I loaded it, add and then write back something, some other processor could actually go and modify the memory location corresponding to x, right. That's called a race condition. You don't want such things to happen. So atomic operations basically make sure that you don't have such problems. They ensure that the load, modify, add all happen guaranteed within your control, okay. So this is fine. It's a good thing to have inside an interrupt handler, and you will find that there are extensive use of atomic operations in most interrupt handlers. As I said, there is something called a spin lock, which again can be used inside IRQ handlers. There is also something called a wake up interruptible, which we will get to in a moment, right. So effectively, in other words, since I cannot do any of this stuff like sleeping, copying data, allocating memory and so on, all of this is considered heavy work, and what we do is that we define something called tasklets, right. A tasklet is sort of a small version of a task, essentially a function call, but something that can be sort of deferred and run at a later point in time. What we do is we tell the kernel, I need you to run this function for me. That function will take care of copying data from A to B, but I don't want you to do it right away. You can take a little bit of time over it. So I put it in something called a work queue, right? And once I put it in that work queue, the kernel, the operating system kernel, will first finish handling the interrupt and then say, okay, now what else do I need to do? Is there some task sitting on the work queue? If so, go and execute it, right? So that is typically how interrupts are able to do more complex work, like copying data around and actually providing user inputs and so on. So the idea of wait queues is, as I said, very important in the context of how exactly we are going to be using the basic structure of doing some heavy work inside an interrupt handler, right? So an example of this would be something of this sort, right? I want to implement what's called blocking IO, okay, and it's some kind of a read operation. An example of this we will look at in a moment, right? Let's say that I set up my timer and I can, so far we have been looking primarily at the so-called platform drivers, which basically give us the /sys interface. But in an earlier video, we had also seen about how we can create the so-called character devices, right? The /dev/vreg demo or /dev/smart timer and so on, right? Now the thing is, what that means is I can actually open that /dev/smart timer as a file and try reading from it. Now that looks interesting, and in particular one very useful place over there is I can basically say I want the reading from that /dev/smart timer to just block until the timer has wrapped around, right, until it has triggered and basically told me that yes, some event happened over here and I want you to go and process it, okay. I don't want to sort of sit over there and wait on interrupts and so on. When I am writing a user space function, right, I am not really, ideally I would not want to go in and modify things at the kernel level. I want something which will directly wake me up as soon as data is ready. So in other words, I want a read operation to be implemented, which will block until the next wrap operation or the next interrupt that happens on the smart timer, and we'll look at an example shortly. The way that we do it is, this part of it, the read function, basically calls this function over here called wait event interruptible, okay. Now what does this wait event mean? It basically gives an extra variable on which we are waiting, right, and this particular variable is a special data type inside the kernel, which is essentially capable of handling events, okay. So the kernel basically will be able to wait on this particular condition. It waits for something to happen over there, and then when there is an event on this particular st-wait, it performs this operation. It reads from wrap count, checks whether it is greater than or equal to some target value. In other words, it performs one Boolean condition check over here, right, and if that condition is satisfied, right, so in other words, if this entire wait event, this condition is satisfied, it means actually that something went wrong, okay, because the way that wait event interruptible works is that it essentially returns 0 if the condition is not satisfied, which means that I would basically just exit and go through to this point. But if it is satisfied, essentially what will happen over here is the entire function will return with this special code, right, this -e restart sys is a enumerated data type, another code. It's basically an integer value somewhere in the kernel, which indicates that something went wrong. Mostly what it means is I was waiting for an event to happen, but I got interrupted instead, okay. So we'll look at look at the actual code and see how it works in a moment, right, but essentially what we are going to do is we'll have to do this thing where we wait for a particular event to happen. Now how does that event happen in the first place? That happens inside the IRQ, right. So inside the IRQ, what I'll do is I'll basically check the status. If the status was actually wrapped, I'll clear it, increment the wrap count, because that's basically what I'm doing over here, and then I will basically say wake up interruptible structure wait, okay. So as you can see over here, this st-wait over here and this st-wait over here are the same. In other words, whenever I wake up the interruptible events over here, what it's telling me is the kernel will say, okay, I'll keep track of all the functions that were waiting on that particular event, and when this happens, I'll go and wake them up, and that function can then wake up and if the condition is satisfied, it will basically come out over here and run whatever it needs to do. Okay. It will basically block, in other words, on this particular point. So, this wait event interruptible won't even return a value until this particular thing has got handled properly. Okay. So, just to sort of review that, right, the predicate is this part over here, this atomic read, etc., right. It must reflect a state variable. In this case, my state variable is the wrap count, which is keeping track of something which is related to the state of the IRQ handler. It can read atomics or locked fields. So, in this case, basically I am doing an atomic read of a parameter that I have over here, right. So, that is okay. So, I can have something fairly simple being computed out here, right. And as I said, this particular, this minus E restart sys is used as a special signal to say that, look, something went wrong. I was waiting for an event, but instead I got an interrupt. I was essentially, this whole thing was broken. So, it is not really satisfied. You go handle it in some other way. Now, all of this depends on the use of this thing called the wait queue, right. So, there is this wait that we have over here, st-wait, right, that both of this, the interrupt handler as well as the blocking read are depending on, which means that it must be some data type that is set up and initialized somewhere. That happens inside the driver probe function.